In the last class, we have done few operations, namely complement, union, intersection, namely fuzzy complement, fuzzy union and fuzzy intersection. Okay. In this class, first of all I will do one thing, that is linguistic variable, and then again I will define this fuzzy complement, fuzzy union and fuzzy intersection in terms of function. Okay. So, these three, fuzzy complement, fuzzy union and fuzzy intersection, will show in terms of function. And lastly, we will do disjunctive addition, some other operation. Okay. Now, let us start with linguistic variable first. Okay. So, linguistic variable means, suppose we define the temperature. Okay. So, temperature I can have, we can say linguistically as very low, low, medium, high, very high. Okay. Again, because as we discussed previous classes, that this very low or low, medium, etc., we cannot define exactly. Okay. So, to define this, suppose this is your T, okay, this is your mu membership function, and I want to designate this VL, L, M, H and VH, those are very low temperature, low temperature, medium temperature, high temperature or very high. Okay. So, let us start. Suppose this is your 0 and this side is negative. Okay. Negative temperatures means very cold, very, very cold. Okay. So, 0, suppose this is 15, 20, 25, 30, 35, 40, 45. Okay. Suppose I am taking from 0 to 50 as the range of the temperature. Okay. Now, first I define very low. So, very low can be like this, I can define, that means minus of any temperature up to 15 degrees, suppose I take degree centigrade here. Okay. So, 15 degree centigrade, this is your very low. Okay. Now, low, low I can have from 0 to 25, it is again user defined, you can have different range. Okay. So, 0 to 25. So, I can plot this like this, 0 to 25. Okay. So, and I suppose that this is 1, this is 0, these are the membership functions. Okay. Okay. So, 0 to 25 I defined as L, low. Now, medium I can have from 20 to 35. So, 20 to 35 means I can define like this, 20 to 35. So, this is I defined as medium. Okay. Now, high I can have 30 to 45, 30 to 45, this is your high temperature. Okay. Now, very high I can have 40 to maybe 40 and above. So, I can draw like this high values. So, you see this linguistic variable temperature for this very low, low, medium, high, very high, I can have the representation like this, okay, like trapezoidal. So, this I will do in greater detail afterwards. Now, these are trapezoidal, I can have triangle also, other shapes also. Okay. So, just to let you know that these linguistic variables I can designate like this in as a fuzzy sets. Okay. So, understood? So, now I am erasing this. So, next we will go again to the fuzzy complement. You remember what is fuzzy complement? Yesterday's class, it was if A bar is a fuzzy set, fuzzy complement, we know that if A bar is a fuzzy set and its membership function is mu A bar x, then we write A bar complement its membership function as mu A bar complement x, and it is defined as 1 minus mu A bar x. Simple negation, 1 minus of that. So, this I will define as a function. Okay? So, for fuzzy complement I define as a function c, okay, from 0 1 to 0 1, because my range is from 0 to 1. Okay? C is a function from 0 1 to 0 1 which satisfies certain axioms, okay, which satisfies the following axioms. Okay? Now, you see, you can see very well from here the axioms. Okay? I am writing one by one. So, first one is axiom 1. See, I have the range from 0 to 1, and you know C of 0 as per the definition will be what? C of 0 should be 1. C of 1 is 0. So, this is called boundary condition. Boundary condition. Okay? Because only the boundaries I am taking first this in this axiom. So, C0 is 1, negation, 1 minus 0, C0, C1 is 0. Okay? This is first axiom. Axiom 2 is if A less than B, where AB belongs to 0 1, okay, then what I can say about complement of A and complement of B? Yes, it is complement of A should be greater than or equal to complement of B. You have seen yesterday's that figure and examples. Is it okay? That means this A and B belongs to 0 1. That means these A and B are nothing but membership function actually. So, if I take in terms of membership function now, so suppose A is mu A bar x, A is, I am supposing A as mu A bar x. A may be also, if you take A means mu A bar A, then you have to define by other variable. Okay? So, A is suppose mu A bar x and B is mu A bar y, two different points. Okay? And if I have A less than B means what? Mu A bar x less than mu A bar y. If this is the condition, then what we will have for complement? Now, then complement of mu A bar x, as we did for this, it will be greater than equal to C of mu complement of mu A bar y. Okay? Clear? It is coming from the same definition of complement, fuzzy complement. So, these are the two axioms, first two. So, these two axioms are called, actually we have 4 axioms, but these two axioms are called axiomatic skeleton. Axiomatic skeleton. So, with these two we have 2 more axioms for this complement function, that is also obvious, and you can see I am writing then the axiom 3 and axiom 4. Okay? So, I have to, so yes, one more thing, this is called actually, this says that C is monotonic function. No, so C is monotonic. Okay? So, we have the first axiom boundary condition, second axiom monotonic. Now come to the third and fourth. Third axiom is C is continuous. This is third. That you know what is continuous. Okay? So, C is continuous. Axiom 4 is if I take complement of A, it will be what? It should be A. If you see in terms of membership function also, you see if I have C of C mu A bar x, suppose. Okay, I can write this C of, because C of mu A bar x is 1 minus mu A bar x, 1 minus mu A bar x, and if I again take complement, so it will be mu A bar x. Again I take mu A bar x, and this is called idempotency. This is called idempotency. Okay. So, these 4 axioms are for complement function, which are you can see from the definitions. Okay. Similarly, we have for union, fuzzy union also, that we will see next. So, fuzzy union, this also I can define by a function. Let us denote by u, because it is union, okay, standard union u, and this function will be from cos 0 1, because it is union, to 0 1. This is your function, and it satisfies 6 axioms. We have 6 axioms with the following axioms. Okay. So, axiom 1 should be boundary condition. So, boundary condition. So, u of, I can take 0 0. So, you know union of the membership function 0 0 will be maximum of that. So, maximum here will be 0. Okay. U of 1 0 1, u of 0 1 1, u of 1 1 1. Okay, simple. So, this is your boundary condition, you write in full, that is called boundary condition. Okay. Axiom 2, if I have A, some membership function A less than A dash and B less than B dash, then union of u function, union of A B should be less than or equal to union of A dash B dash. Okay. This is again monotonic, monotonic. We have third axiom, commutative, means I can have u of AB is equal to u of BA, because maximum of AB is the maximum of BA. Okay, same thing. So, I can write this. Fourth one should be your standard associativity. Okay. Axiom 4, associative. Associative for this function u of, suppose u of, I take 3 numbers A, B and C, means I take the u of AB, get the result, suppose P, and then again take u of PC, whatever result you will get, if I do u of A, u of BC, means first you take for these 2 and then this and this, the same result you will get. Okay. So, associative follows. So, this 1 to 4 are again called as axiomatic skeleton. Okay. 1 to 4, axiom 1 to 4. So, we have 2 more axioms. Okay. And you know same, axiom 5 is u continuous. Okay. And axiom 6 should be u of same element A will be A, maximum of A is A. Okay. And this is called idempotency. Earlier, yes, 1 minute, idempotency, let me get idempotency, yes.
Why commutative axiom is not defined for
complement? Complement there, what it was? Function, you remember, there this cross was not there. How will you do that? He is asking why in the complement function this commutativity is not there, because there we are operating on only one element, okay, because the function was from 0 1 to 0 1. Okay. So, that is why if you see in the next fuzzy intersection you have these in terms of intersection function. Okay. Okay, so actually if you see in crisp also union, you know actually this is a OR logic or not. So, but if for the union, fuzzy union also it is OR logic. If you see in terms of that tautology, those things are there, I will do afterwards. So, this is also a OR function, OR logic. Okay, means if you say suppose that same example young and old or young and senior, find the young union what was the senior. So, you will get young or senior. Okay. So, if you have understood this, next I will okay. Now, from fuzzy union we have different operations of union also. So, it is given by different researchers. So, there are many, I will write 4. Okay. So, I am erasing and I will write one by one. So, other union operations. So, first one is algebraic sum, and we denote this by A plus, this is just notation, B bar. Okay. A bar and B bar are two fuzzy sets, and what is the formula for algebraic sum? Formula means main thing is your membership function. Okay. So, membership function they defined as mu A bar plus B bar x is equal to mu A bar x plus mu B bar x minus mu A bar x into mu B bar x. Okay. This is the definition of algebraic sum, and I will not do, but you can check on those 6 axioms. Some of the axioms will satisfy this. Okay. You will see that those commutativity, whether it is satisfying or not, you can check. Okay. Okay. The boundary, suppose I take boundary. Okay. So, you take 1 0 etc. So, you see whether this is satisfying or not. Okay. Similarly, we have second union operation, that is called bounded sum, and we define bounded sum like this, A plus B, A bar plus B bar, and this should be your for all x. So, here we define for all x membership function A bar plus B bar x is equal to minimum of 1 comma mu A bar x plus mu B bar x. This is the definition for bounded sum. Okay. Third is your drastic sum, and this we denote by like this, A bar union dot B bar, and we define this as mu of A dot B bar x is equal to mu A bar x when mu B bar x is 0, okay, and mu B bar x when mu A bar x 0 and 1 for others. Okay. These are the 3 union operations. Similarly, fourth one we are having, there are others, I am not covering those. So, I am erasing the first one, and fourth one is Hammacher's union. Hammacher's union or sum, because these are all union actually, union operations. It is A bar union B bar, and we define this for all x belongs to x, these will all belongs to x, mu of A bar union B bar x is equal to mu A bar x plus mu B bar x minus 2 minus gamma, gamma is a parameter, mu A bar x, mu B bar x, this is a little bit lengthy, divide by 1 minus gamma, mu A bar x, mu B bar x, and gamma greater than equal to 0. So, these are different operations for union given by different researchers. Okay? So, sometimes mu sets may be given, okay? Those memberships may be given and it may be asked to find Hammacher sum. Very simple, just put the formula and get. Okay? But those are used actually practically. We will see whether we can get time and to define all those things. Okay. So, similar to fuzzy union, next is your fuzzy intersection. Okay. Fuzzy intersection. Again I can define this in terms of some other notation I. Okay, I from 0 1 cross 0 1 to 0 1. Again we have 6 axioms here, okay, similar to your union, little bit change as per the definition of intersection. So, axiom 1, boundary condition, I of 0 0, intersection means minimum, we know. So, 0 0 0, 0 1, here it is 0, not 1, in union it was 1, here minimum, so it is 0. I of 1 0, 0, I of 1 1, 1. Okay, simple. So, this is your boundary condition. Axiom 2, again if A less than A dash and B less than B dash, then I of AB less than equal to I of A dash B dash. Okay? And this is your monotony. Okay? Axiom 3, axiom 3 was commutative. Commutative, that means I of AB is equal to I of, just other way, that is BA. Okay? Axiom 4, that is associativity or associative. So, I of AB comma C, okay, is equal to I of A comma I of BC, means order is not important. Yes. Which one? Axiom 2. When will this? See, A less than A dash, you think about the membership function. Okay, these are not AB, AB belongs to 0 1. These are not the numbers. Okay, he is asking when it will be equal, because here no equality is there. But you think about the membership function and its complement, sorry, not complement, means union, intersection, whatever is there. So, if you think in terms of that, because I have to write mu so many times, so that is why I am taking A and B. Actually A, B are your membership function. Okay. So, associative. So, these 4 again are called 1 2 4 what? Axiomatic skeleton. Okay. Then we have axiom 5, I is continuous, and lastly axiom 6, it was I of same element A or same membership function, it is your A, and the name is same again, idempotency. Okay, similar to union, we have some other operation, same name, but it was sum, algebraic sum, then bounded sum, then drastic sum and Hamacher's sum or Hamacher's union. Same, it is algebraic product, only those will be all product. Okay. So, if you want, I can write those formula or you can get from your book. Okay. Should I write? Okay. So, you try, otherwise next class I will write. Okay. So, we have similarly the other intersection operations, those are algebraic product, then bounded product, drastic product and Hamacher's product. Okay. In place of sum, those are product. Okay. See, why these all are means different types of union and intersections? Because see, I told that again same example, that if you have a matrix A, fuzzy matrix, I cannot find in general A inverse. Okay. But few researchers have tried this using their own definitions. Okay. So that they can avoid those things, that I wrote A intersection A complement is not phi, like that. Okay. So those things, those are there, actually you will see afterwards that what is the difficulty in finding these, you will see slowly when we will come to all those problems, etc. Okay. So that is why people are defining different types of union operator, intersection operator, because there you have the difficulty enough. Fuzzy is not a crisp one, if boundary you do not have exact boundary. Okay. So that is why they have given different definitions. So next is disjunctive sum. So disjunctive sum you should know in crisp set theory. Anyone knows? Disjunctive sum. Have you read? Yes, yes. Complement is there. See, this is actually, as I told that union is actually OR logic. Okay. So, I am giving you hint, it is exclusive OR. This is actually exclusive OR, disjunctive sum. So, if I am showing by this figure, suppose I have in crisp A is a set, B is a set. Okay. So, disjunctive sum is this area, now you define, except this. No. Yes. Yes, she is correct. She is correct. I know, but see, this is defined as A for crisp, A plus B, crisp. That is why I am writing AB. Okay, I have just removed bar. A plus B is equal to A intersection B complement union A complement intersection B. You see, A complement is how much? This. Okay. And B complement is this. Now you take the union, intersection of that, A intersection B complement, union A complement, intersection B complement. Okay. So in fuzzy, for fuzzy disjunctive sum, it is same. We have two types of sum actually. One is simple disjoint sum and other is just disjoint sum. Okay. One is simple disjoint sum and other one is disjoint sum. First let us define simple disjoint sum in terms of, because see, when we have fuzzy, again we have to think about the membership function. Okay. Element is your crisp till now, but element again may be fuzzy. Okay. And moreover you are giving, we are giving ordered pair as x mu a x. Mu a x, when you are putting the number, that is crisp or not. Suppose 0.5 you are telling, that is crisp, but that 0.5 may also be fuzzy. So, there is n type of fuzzy, means type 2, type 3 fuzzies are there. So, more complication will come. So, simple disjoint sum I will write like this, same A plus A bar plus B bar, just I am replacing by bar, okay. A bar intersection B bar complement union A bar complement intersection B bar. So, here you know, if I have for A membership function as, for A if I have the membership function as mu A bar x, for B bar if I have mu B bar x, then for A bar complement we write as 1 minus mu A bar x, standard notation definition, complement I write 1 minus of that. Similarly, B bar complement I write as 1 minus mu B bar x. Okay. Now, what will be A intersection B complement? That means for membership function of A intersection B complement of x, it will be minimum of what? This and this, okay. Minimum of mu A bar x comma 1 minus mu B bar x, okay. Similarly, I can have membership function for A bar complement intersection B bar x, okay. This again will be simply minimum of 1 minus mu A bar x and mu B bar x. Is it okay? So, simply then I can write for whole maximum of mu A bar plus B bar x is equal to maximum of this term and this term. So, if I write this as maybe P, this as Q, so maximum of P and Q, okay. So, in this way we can find simple disjoint sum for fuzzy sets, okay. Let us take one example. Suppose I have a fuzzy set A bar as x1 comma 0.2, x2 comma 0.7, x3 comma 1, x4 comma 0. This is a fuzzy set. You have elements x1, x2, x3, x4 having membership values 0.2, 0.7, 1, 0, okay. And B bar as x1 comma 0.5, x2 comma 0.3, x3 comma 1, x4 comma 0.1. So, let us find the disjoint sum, simple disjoint sum, okay. So, first I have to find A bar complement. So, you know I already defined yesterday's class, A bar complement will be x1 comma 0.8, x2 0.3, x3 0, x4 1. This is your A bar complement, okay. Now, B bar complement x1 0.5, okay, x2 0.7, x3 0, x4 0.9, okay. I have to find now A1 intersection B1 complement, B complement, sorry, A bar intersection B bar complement. So, find that A bar intersection B bar complement. You know what to find? You know intersection definition. So, I have to see this and this. So, take x1 element and minimum of this. So, it is 0.2, then x2 what 0.7, x3 0, x4 will be 0. Yes, good. Now I have to find A bar complement intersection B bar. That means this and this. So we will have x1 and 0.5, correct? Then x2 0.3, x3 0, x4 0.1. So very simple. Only minimum we have to take. Now find the sum, disjoint sum. That means A plus B. And you know the definitions, union of these two. So that means we have x1 maximum of these two, it is 0.5, okay, x2 0.7, then x3 0, x4 0.1. Okay, very simple. So this actually you can see geometrically what is happening also. Okay, suppose I have this fuzzy set, so I can erase from here. Okay. So you can plot this. Suppose this is I am plotting A, so I have x1, x2, x3, x4. I have from 0 to 1. First one is x1 0.2, suppose this is 0.2, so I can have like this. Okay, it is going up to 0.2 in the mu direction. Okay, this is your mu. Second is x2 is 0.7, so if it is 0.5, so maybe it is 0.7. So x2 it is going like this, so I can change this to x2. Okay. Then x3 is 1, so maybe this is 1, and then x4 is 0. So this is the plot for this fuzzy set A, for this, because it is discrete. Okay. Okay. Now similarly you can plot for B bar, this is your A bar, and then plot for this. So you can see what is happening, okay, geometrically also. So this was for simple disjoint sum. So another one is only disjoint sum, that is very easy. So let me put this, because these examples I need. Disjoint sum. Here we define this and we denote this by this disjoint A delta B. Okay. Okay. So here this membership function is defined for disjoint sum very simply like this: absolute value of, this is all bar, okay, mu A bar x minus simply mu B bar x. Okay. So it is very simple, in one step you can get this mu or the disjoint sum fuzzy set. So then it will be only minus absolute value. So it will be 0.3, x2 it will be 0.4, x3 it will be 0, x4 it is 0.1. So this is your disjoint sum. Okay. Okay. So thank you. So next class we will do further other fuzzy operations 2, 3.